All right, section 1.3 is reasoning and logic. And what we're going to start out talking about some sort of definitional things. To start with, a sentence, or statement, excuse me. A statement is a sentence that is either true or false. So, for example, a statement would be something like, I ate cereal for breakfast. Now, I didn't this morning, so it's a false statement, but we can actually say it's either true or it's false. The non-example there is, what did I eat for breakfast? That doesn't make sense to say true or false to it, right? I mean, like, it doesn't even make any sense. So questions are not considered statements. Neither are commands. So if it's, eat your breakfast, that's not a statement either. That's a command, okay? So statements have the ability to say that they're either true or they're false. A negation for a statement. First of all, if a statement, for instance, if we use the letter P to be our statement, then not P is the negation, and it's this little tilde. It's not very big on there, but it looks like, oops, I've got my highlighter still on. It looks like this. It's on a keyboard of a computer as well. It's a tilde P. We read it as not P. It's kind of like having a negative or something like that. So the negation of I ate cereal for breakfast would be I did not eat cereal for breakfast. It's the exact opposite. Now, sometimes negations are very straightforward and sometimes they're not. This one was very clean. Obviously, you look at those and you say, yep, I either ate cereal for breakfast, I did not eat cereal for breakfast. Exact opposite. But they're not always that clear. So let me talk about when they're not that clear. In particular, they're not that clear when they have what we call quantifiers in them. There are two types of quantifiers. Universal quantifiers and existential quantifiers. Universal quantifiers refer to each and every element in a set. So you see words like all, every, no, none. They're the words that your mom told you to avoid when you were saying, every time I do this, something happens. You never do this. Okay? Those are the words we're talking about here. They're universal quantifiers. Existential quantifiers, for example, all people are sinners. All excludes no one. Every single one. So if you tell me I'm a person, I can tell you you're a sinner. That's the idea. Existential quantifiers refer to one or more elements in the set. So you see something like there exists, or some, or sometimes you'll see the phrase at least one. So if we were talking about this class, we cannot say in this particular class that everyone in this class is female because there's at least one person who's not, and we happen to have two in the class right now, right? But this is not always common, right? I told you this is the first time this has happened to me. My other elementary math class is all female, actually, right now. So we have the words some in this one. So some cats go to heaven. At least one cat goes to heaven. There exists a cat that went to heaven. Those kinds of phrases. So you see those phrases, you have an existential quantifier. Now, the reason for mentioning these in particular is because when these kinds of words are present, creating a negation becomes more complicated. Okay? So, we're going to take a look at why that happens. So, here's an example. All dogs go to heaven. All right? So what is the very bare minimum thing that has to happen to make this statement false? One dog doesn't, right? If just one dog doesn't end up in heaven, the statement is now a false statement. That's all a negation is. It's changing the very least amount of stuff possible to make the statement opposite of what it already is. So we could say at least one dog doesn't, or does not if you prefer, doesn't go to heaven. You don't have to use the phrase at least one. You could say some. That'd be okay. Some dogs don't go to heaven. I know that sort of sounds like it's more than one, but that's all right. We still can use that. And then, so that took something. Notice what happened when you did that, though. What kind of a quantifier is the word all? It is universal. And what kind of quantifier is the phrase at least one? Existential. And that will always happen. And I used the word on purpose, yes. Always. So the way that we change a a phrase to its negation is that we switch universal quantifiers into existential quantifiers, and vice versa as well. So you take a look at the next sentence. The next sentence, or even statement rather, says, some of my classes this semester are hard. Is this got an existential or a universal quantifier in it? Existential. It's right here, right? So in order to change this to its negation, I have to change that to the other type of quantifier. It's a requirement. So the word some has to become what? All or none. Those, and you can create it either way, depending on what you're going to say next, okay? So one of the two statements has to be happening next. Or probably no would be better, based on the English that we're using in here. So all of my classes, or, no, I was right the first time. None of my classes. I think that was better, wasn't it? None of my classes, yeah. So none or all of my classes. All of my classes. Or none of my classes. And then whichever one you pick, and they're both equally acceptable, will depend on what you say next. So if you pick all of my classes, what would you say then next? Just be careful on that. We don't want to say are easy, are not hard. Because I would contend that there are probably classes you've had that would be neither easy nor hard. So we're just trying to say that they're not hard. Okay? I have certain classes that I wouldn't say are easy, but I would definitely say are time-consuming. They weren't hard, but man, they were time-consuming, which is something different. If we chose to say none of my classes, what would we end with? None of my classes are hard. So notice the ends of these are different, right? Because the beginnings were. They have to be. And they have to be the opposite of what we were trying to convey, the opposite information that we were trying to convey with the original statement. So, all of my classes are not hard, or none of my classes are hard.
You can't say all of my classes are hard.
Well, all of my classes are hard would not be a negation. It would be a stronger statement than I started with, not an opposite statement from what I started with. Right?
Okay.
And that's the reason. But I'm glad you mentioned it, because a lot of times people will make that mistake. So we definitely have to change the quantifier, but we also have to make the statement the opposite of the statement we have. Okay, so if we said all of my classes are hard, well, then some of them certainly are hard. All of them are. It's just a stronger statement we had before. All right, truth tables. Truth tables are a logical way of organizing information, showing all possible true, false patterns for statements. Okay, so we're going to create a very simple truth table to start with for a negation. So truth tables kind of look like a T-bar, or an XY ordered pair set or something like that. And we're going to put P because that's our statement. And it says we're going to do negation here, so we're going to do tilde P. That's the notation for that statement. So the way it works is this. We write down every possible thing that could happen in terms of being true or false for our statement or statements. So we could have, I'll use capitals, that's what I'd usually do. Capital T, our statement could be true. Or our statement could be false. I mean, those are the only two things that could possibly happen if I've got a single statement. So when I had that statement that said I ate cereal for breakfast this morning, it's either true or it's false. There's no middle ground. I either did or I didn't. Okay? Now tilde P is actually saying I want the opposite of, the negation of. In other words, if the original statement was true and you had the negation, it would be false. And likewise, if the original statement was false, the negation would be true. So negation truth tables are very straightforward. Whatever it was before, you switch it. Compound statements are two statements that are joined with connectives. Connectives like and, or if then. Those are the three connectives. Occasionally you'll see a connective with the word but usually means and. Right, somebody says something like, my oldest daughter likes to use the word but. So we'll say, are you finished with your homework? She said, I am, but. She means I am and is what she really means. When we use the word but, we usually mean the word and when we're combining statements together. Just try it next time you use it and see what happens. So there's two types of, the two we're going to talk about first are conjunction and disjunction. And then I don't have a slide in here for the if-then, which we'll do in a minute. But a conjunction is the equivalent of an and statement. Okay, so things that are and. So something like, I am a math professor and I am a mom. Two statements, completely, disjoint. They're not really related together, right? You could be one or the other. You could be both. You could be neither, right? And that's the statements, okay? So let me show you how a truth table works. And I'm going to show it to you, and then I'm going to argue with you through why it happens. So let's start with our two statements. So the only way we can have a compound statement is, in fact, to have two statements. We're going to use the statements P and Q. So one possibility is that both statements are true. Yep, certainly. Or we could have the possibility that the first one's true and the second one's false. Or we could have the possibility the first one's false and the second one's true. Or they could both be false. So when you're creating these truth tables, and we'll create more later, what you'll begin to notice is that the P and the Q column are always set up the same. I always go true, true, false, false, and then I alternate true, false, true, false. It's a pattern. You're always going to have it the same. The nice thing about it is that means that you already know part of the answer when you're starting the problem. I mean, it's because it's always the same. The next column is going to say P and Q. The and symbol is an upside down V is kind of what it looks like. Okay, so we're going to argue our way through what of these statements have to work. So I gave you a compound statement just a minute ago. My compound statement said, I am a math professor and I am a mom. Okay, so if I walk in here and I say I'm a math professor and I'm a mom, both of those individual statements are true. So me saying them together with the word and in the middle means that I still said a true statement. It is still true because each of the individual statements were true. All right.
Can you say that again?
Yeah.
Okay.
So my example that I'm using is I am a math professor and I am a mom. So if you heard me say that statement and you knew both of those pieces of information were true, that would mean we're on that first line here, then me saying it all together with the word and in the middle would also be true. I could say I'm a math professor and I'm a mom, and I would be telling you something that's a true statement. Okay? Now, if, who knows Dr. Auk? Okay, a lot of you do. Dr. Auk, Tanner Auk, male professor in the math department, just for those of you who don't know, okay? Dr. Auk, if he walked in here and he said, I'm a math professor and I am a mom, yes, you might laugh at him, but you would say that that statement would be false because part of it was not true. Correct? Yeah, not going to work. All right, now let's say that trying to think. I don't know if you know, but Dr. Turnage is a female professor over in computer science. She's a mom. Okay, so let me just a little bit of background. Pretend she walks in here, okay? She's a mom. She's a computer science professor. So she walks in here and she says, I'm a math professor and I'm a mom. That's also false, right? Because she isn't a math professor. She's not. She's a mom. That part's true. So this is why we're on this line, right? The first one would be false, not a math professor. The second one would be true, is a mom. But her saying them together in the same sentence with the and in the middle makes it a false statement. All right. That's the one I'm going to use. Very good, Skylar. Dr. Whitlock walks in. Yes, he does. And he says, I am a math professor and I'm a mom. No, that's just not going to work for us, is it? Definitely false. Both pieces of information are false. So what you see over here is that a conjunction is true only if both of the statements are true. And that's exactly what our truth table shows, right? We only have one true in that final column. All right, we're going to use all our same people again and all of our same stuff again, but we're going to join them again instead, with the word or. This is called a disjunction. So our table looks very much the same, P, Q. Over here, instead of that upside down V, we have what kind of looks like a right side up V, P or Q. All right, so again, we have the possibility of being both true, the first true, the second false, the first false, the second true. Make sure your T's and F's look a little bit cleaner than mine. That's not very good. Sometimes it's hard to make them look different, so if that's you, be careful. And then the last one's both false. All right, so again, if I walked in and I said, I'm a math professor or I'm a mom, you would say, true. Yeah, you are. I mean, it sounds a little awkward to put the word or in that particular sentence, but it's true. Who did I use? Dr. Hauk, that's right. If Dr. Hauk walks in and says, I'm a math professor or I'm a mom, it's true. Again, it sounds a little awkward because the part of it's actually false, but it is a true statement. He is one or the other. If Dr. Turnage walks in and says, I'm a math professor or I'm a mom, it's true because she is a mom. If Dr. Whitlock walks in and says, I'm a math professor or I am a mom, that's still false because both of the individual statements were false. So an or statement is true if either statement is, or both. I put that in parentheses because either means both, but sometimes we don't think of it that way. If either statement is true. All right, so what we're going to do next is we're going to create a couple of truth tables for just, without sentences or anything like that, just to work on the truth table part of it, the logistics of that. So we're always going to have a column for each of our statements. So we've got a statement that's P and a statement that's Q. Okay, so if there's a P in the problem, there's a Q in the problem, they're going to each have their own column. The next thing you're going to do, oftentimes anyway, and look to see if there's any negations. Now we don't just want to put every negation possible. We only need what's there. So there is a negation here. It's a negation of Q, so it's not Q, exactly. And then we notice we've got all of the individual pieces that are in our problem, and then they're combined into a conjunction, that is an and statement. So this is P and tilde Q. Okay, so again, the beauty of truth tables is that you know how they start. They go true, true, false, false in the P column, and they go true, false in the Q column. All right, then what's the negation of Q going to be? False, true, false, true. Exactly. So the next thing we're going to do is we're going to compare the two columns that are present up here in this description. That is column P and column tilde Q. So comparing those two purple highlighted columns, when is an and statement true? When they're both true. So on the first row, when I have a true and a false, I would actually get a false result. On the second row, when I have a true and a true, I get a true result. Third row, I have a false and a false, I get a false result. And the fourth row, when I have a false and a true, I get a false result. That's a truth table. Now notice the directions here. This one said to create a truth table, right? Which is exactly what we did. I draw your attention to that because it doesn't say that on example 3. What does it say we're supposed to be finding? A truth value. Now you can do that with a truth table. There's nothing wrong with that except that it's way more work than you're actually asked to do. I don't know about you, but I don't want to do extra work than I'm asked to do. I have things to do that are more important otherwise, don't you? Yeah. So what does it mean to ask for me to do a truth value instead? Well, in reality, it means I'm going to do a truth table, but it's only going to have one line instead of these 4 lines. Okay? Now, it's going to still have the same column headers and everything as before. So if I had a P, I'm still going to have a P. If I have a Q, I'm still going to have a Q. You notice you've got 2 negations here, a tilde P and a tilde Q. So you're going to have all of that. And I do expect to see this written out. I mean, some people do it other ways, and that's fine. But I want to do it this way because it keeps your organization the same as when you're doing truth tables. It's the most clean way to keep them all organized. And then, okay, so let me draw this. And then you're going to have the last column header that's P tilde P or tilde Q, right? That's the combining of everything at the end because I had all the pieces up to that point. So what do we do in terms of trues and falses? Well, we use the given information. They actually tell us P is false. And they tell us Q is true. So we put that information in. They didn't do that on the problem before, right? No, because it wanted us to create the whole table. This one's not asking for a whole table. They're telling us the piece of the information that they want. All right, so if P is false, what's tilde P? True. If Q is true, what's tilde Q? False, an F, yeah. And so then on the last column, I'm trying to combine the tilde columns, the tilde P and the tilde Q. And I'm combining them with an or statement. So what does it take for an or statement to be true? At least one of them true. Do we have that? Yes, so this statement is true. Now, here's the deal. The answer to the question is true. I mean, it should be the last column of your truth table, but I want you to actually recognize that you found a result. Your answer is true. So either box in the last T, write out the word true, something to indicate that that was all my work, and now my answer because of all that work is this. True. Okay, are we all good? Hang on just a second. All right, yeah, we'll get there in a minute. Okay, logically equivalent. Two statements are considered to be logically equivalent if they have the same truth value in every possible situation. Okay, so like if you were to create a truth table for two statements and they ended up at the very end all exactly with the same T's and F's in the same places, they would be a logically equivalent statement. And I'll show you an example here in a minute. The way that we write that is we write it with 3 lines, kind of like an equal sign, but there's 3 lines between the P and the Q. I know it's really small, but it looks like this. Okay? De Morgan's laws do in fact create just that. They create they give us 2 statements that are logically equivalent. So let's actually talk about what those statements say, or kind of observe what you're seeing. All right, so the first one has P and Q inside of a set of parentheses, right? And they've put a tilde on the outside. And then on the right-hand side, it sort of looks like the tilde has been sort of distributed through, because now there's a tilde on the P and there's a tilde on the Q. But what else do you see that's happened? It's an or statement. So it's actually changed from a conjunction into a disjunction. That changes when you sort of distribute this negation through. And the same works when you start out with an or statement. If you distribute the negation through, so to speak, you would actually change from an or statement into an and statement. So if you're taking a look at De Morgan's laws and you're actually trying to find the negation of this one right here, that is the negation of P and tilde Q, and you're sort of thinking about this idea of distribution, because we think about that pretty well, you actually distribute it sort of to 3 things. So you get the negation of P, which is tilde P. You get the negation of and, which is or. And then you get the negation of tilde Q, which would be Q, right? Yes, you could. If you didn't, it would be okay.
Oh, wait, why is it just Q, not tilde Q?
Because it already was tilde Q.
Oh, right.
Yeah, it started out that way. Okay, I'm sorry. Yes, that would be the answer. The next thing I'm going to do is I'm going to actually show you that it actually really is the answer. That is to say that these really are logically equivalent statements. That is that it works. Okay? So, example 5 says to verify that they are both, verify that both tilde of P and tilde Q and your answer, the answer we just got obtained in number 4, are logically equivalent. So the way that we do that, the way that we prove something is logically equivalent, is we create 2 truth tables. We create one for this statement right here, and then we're going to create a second one for our statement that was tilde P or Q from the previous page. Now, in theory, could we put them into the same truth table? Yeah, we could. It starts to be a little bit confusing looking at it that way, though, so I'm going to do it in 2 truth tables separated so that you can really see the physical effect of what's happening in there. So taking a look at example number 1, this one's actually, not example 1, I mean this, the first number 1 where I put that on there. This one's the one that's a little bit more difficult to put into a truth table. That is, it's going to have more pieces. And the reason it's going to have more pieces is because of those parentheses, okay? So I'm going to have a column for P, a column for Q. So let me write those in. There's P and there's Q. Now, we're going to work just like in algebra and things like that. You're going to work from the inside of the parentheses out. So looking inside of the parentheses, what do you see? P, which we already have, and you see negation of Q. So I need a negation Q as well. And then you also see, what you guys said also, is an and. So these are the individual pieces that are inside of my parentheses, and then you see them joined, that is P joined with tilde Q, and it's joined with the conjunction and. But then what happens? You have to negate it, right? There's one more step. It's the negation on the outside. So we end up with another column that negates all of this. That it's the negation of P and tilde Q. All right, so walk me through. What's going to go in my column P? Fantastic. What's going to go in column Q? True, false, true, false. What's going to go in column tilde Q? Perfect. Everybody good so far? Great. Now we've got an and column, and I love highlighters on this thing. I think they're fantastic because I can just make sure you guys are all seeing what I'm seeing when I'm looking at it. These are the two columns that apply to my and statement, right? Yeah. So we're going to look at those two. When is an and statement true? When they're both true. So in the first row, I have true, false, so that gives me my second row is true, true. My third row is false, false. And my fourth row is false, false. I'm sorry, it's false, true. False. That's false. And then what am I supposed to do then in this last column?
Just negate it.
Yeah, just flip them all, right? Switch them all. So instead of it saying false, true, false, false, it's going to say true, false, true, true. Excellent. And that is one of our truth tables. Now we're going to do the other one. The other one's got less going on because it doesn't have parentheses. So we're going to have at least one fewer column in it. I do need a column for P and Q. There's my P column, my Q column. What else do I need a column for? Negation of P. Yes, I do. What else? Yeah, the whole thing. Negation of P or Q. So this is a short truth table to deal with. All right, so what goes in the P column? Q? All right, how about negation of P? Right, false, false, true, true. And then on this one, I'm comparing the tilde P that I just created with the Q column, and I'm using a statement that includes or. Yeah. All right, so or is true when? When there's at least one true. So the first row says true, false. The second row says false, false. The third row says true, true. The fourth row says true, false, true. And we notice what? Yeah, this and this match. And that's why they're logically equivalent by definition.
Is this like proofs? But
It's like a proof. It's a proof of the truth table. Yeah, it's doing it a different way, but yes, it is. All right, so let's do a real life example of the way De Morgan's laws actually work, and you're going to be like, oh yeah, I do that all. I mean, that makes sense. I get it. All right, so here's an example. It is not sunny, and I will go for a walk. We could say that today, couldn't we? Is anyone going to do that? Going to go for a walk today? No, I'm not either, but we could say that. All right, so we want to say the exact opposite. We're going to negate this statement because we aren't planning to do that, right? So the first statement it says is, it is not sunny. So we negate that, and we would say, it is sunny. The next thing we see is the word and. So we'll change that to the word or. And the last statement says, I will go for a walk.
So we want to switch everything, including.
Yep, that's right. And the reason is because a negation is supposed to be the bare minimum that has to be false to make everything, not work. Well, what would it take for it to be false? What would it take for this statement, it is not sunny and I will go for a walk, to be false? Well, it would take one of those pieces to be false, right? So the first piece being false would mean that it is sunny. The second piece being false would mean I'm not going for a walk. And either one of those being that new statement that we just created would be enough to make the original statement incorrect or false. So that's what you have. Okay? All right. Let me show you this slide, and I think then we'll pause for today. Okay? Yeah, I think that's a good spot. Okay, so conditionals are our third type of connective. Okay, so we had one connective that's the and, it's a conjunction. We have one connective that's the or, that's a disjunction. And then we have this connective that's a conditional, it's the if-then. So it's a statement that's expressed by saying if blank, then something else. So the if part of the conditional is called the hypothesis, so that's P. And the then part of the conditional is called the conclusion, and that's Q. And what I want to show you real quick before we conclude today is what the truth table looks like for this, and then we'll stop. Okay? The truth table for this can be it feels awkward. Let me just say it that way. So it starts out the same as any other truth table. You're doing P, you're doing Q, you're doing true, true, false, false, true, false, true, false. All that's just the same. And the way you do a conditional is that you have this arrow involved. If you do, in fact, see an arrow that goes both directions, it means if and only if. You've heard somebody say something like that probably, something like, you will get ice cream if and only if you finish your homework, right? Something like that, if and only if. It just means that you could say the statement in either direction. You could say, if you do your homework, then you'll get ice cream. If you get ice cream, then you do your homework. Something like that. All right, so we're going to draw this with an arrow down here. I'm going to write the values in, and then I'm going to tell you how they work, because this is the one that feels the most awkward. The first three are true, and the last one's false. That's not true. I wrote it wrong. My apologies. Why did I do that? The first one's, the second one's the only one that's false. There we go. Ah. Okay, so you probably don't have any problem with the first line making a true statement, right? I mean, of course. I mean, like if you have two statements and they're both individually true, the if then seems like it should be true. It worked for conjunctions, worked for disjunctions. That's great. The problem is that it doesn't always work very cleanly for the other cases. So if I said something like, if you do your homework, then you get ice cream. And you do your homework and you get ice cream, well, sure, yeah, true, right? But you can't do the homework and expect to get the ice cream. That's going to be a false statement, right? If you do the homework, you know you're getting ice cream. So you can't end up in this column and still actually make sense of that, right? If you did that, you'd be mad. Somebody says, if you do your homework, then you get ice cream, and you do your homework, and then all of a sudden there's no ice cream around. You're disappointed, right? So what are you guys thinking about?
It's not sufficient.
It's
necessary, but it's not sufficient.
Yes, exactly. That's a very good way of thinking about it, yes. So it's necessary, let me say the words you used, it's necessary to do your homework, but it's not sufficient that you actually get the ice cream. This would be a false statement. The last two are the most awkward. Excuse me. What the last two are saying is that you didn't do your homework. Okay? Well, nobody said what would happen if you didn't do your homework. Right? I mean, like, that's not what we mean usually when we tell it. I mean, when I tell my son this isn't what I mean, right? If you do your homework, then you get ice cream. I don't always mean that he's not going to get ice cream anyway. It's just a bribe, right? I mean, like, let's be honest. I mean, that's what we're doing. We're bribing. We may or may not be getting ice cream regardless. So you don't know what's going to happen next. And so kids that are like my son and they're really strong-willed, they want to see. And they may just not do their homework just to see what's going to happen. So you have no way of knowing if you're going to get the ice cream or not. So could you get the ice cream if you do your homework? If you don't do your homework? Yeah, you could. It might be one of those, mom was just pretending. Or you might not as well. And then you would have the second scenario. So both of the bottom two are possible things that could happen. And you have no way of knowing whether or not they happened or not in that statement. So it is possible. They are a possible true statement. Sometimes I give the example, I'm trying to think of how I word it. This is the way I word it. If I'm a mom, then I'm a woman. Okay? So if somebody's standing out in the hallway and I tell you, this is my friend and this person is a mother of 3, you automatically know they're a woman. Guaranteed going to happen, right? It's the first column. Okay? But if I tell you the person out in the hallway is not a mom, they may still be a woman and they may not. Right? That's the last 2 lines of this truth table right here. You have no way of knowing what the result's going to be. Either result could be true. So we put them both down as true. However, if I tell you the person out in the hallway is a dad, you know they're not a mom. I mean, you know they're not a woman, right? It's not going to work out. So that's the second line right there. And that's why that second line would be a false statement then at that point. Okay? We'll stop there. We'll pick up some more with conditional work next time.